Welcome everyone, my name is Maximilian Schwenger and this is the tutorial Monitoring Cyber-Physical Systems from Design to Integration. Something that unfortunately happens rather often in runtime verification is that we have a full-fledged cyber-physical system and we pretty much tag a runtime monitor on top of that after the fact. And this is problematic because it kind of hinders the monitor in unfolding its full potential. So what we are going to explore in this tutorial is how to integrate runtime monitoring in the development process of the cyber-physical system, starting from the design phase up to the full integration at the end. For this tutorial is separated into 3 blocks. In the first block, we are going to talk about the specification. So what kind of properties are there and what differences are there? How do we have to treat them? We will do this on the example language of RT-Lola, a stream-based specification language. And we will see how type checking and interpretation helps us in developing the specification. In the second block, we will talk about how we can get an executable piece of code or hardware out of the specification. And for this, we will see how to compile the specification into VHDL, so a hardware description language, or into Rust code. And in the last block, we will talk about the integration and postmortem analysis and how monitoring can help there. Okay, so in between these blocks, sometimes there is a short break where you can ask your question. We have, I think, 5 minutes for that. So yeah, you can use this chance. Now let's first talk about our setup. In our setup looks like this. We have a system, and the system consists of a cyber-physical system and a controller. Now this system produces values. Where these values come from doesn't really matter. It's either sensors of the system or control signals generated by the controller. And this information is passed on to the monitor. The monitor itself is based on a specification. And before deploying the monitor, we analyze the specification to get an idea how the monitor is going to behave during runtime. Now the monitor takes the input from the system and evaluates it based on the specification to get an estimate on the health status of the system. And this estimate can then be, once again, forwarded to the system, so the system can react and initiate mitigation procedures, for example. So this is our general setup. So we have an external monitoring approach here. Now, let's start with the tutorial by diving right into the specification part. When we want to write a specification, we first have to check what kind of properties we have, because properties are on a spectrum between more low-level and concrete specifications, which we call the sensor level, and the more abstract level, which is the mission level. On the sensor level, you find properties that validate data from different sensors. So for example, and the specification would be, we want to check that the altimeter only produces positive values. On the mission level side of things, things are more abstract, and it more depends on the mission itself. It's not so generic. So an example here could be, we want to check whether there is a low correlation between the distance of waypoints and the relative path deviation we have from the path we computed. Now, an interesting thing here is that the data validation is really time critical. So we get new values from the sensor and we want to immediately get a verdict whether this value makes sense or not. And this information is then used throughout the entire CPS. And if the monitor takes a couple of seconds to decide this, then this value might have already reached the controller and caused a couple of bad decisions. So here timeliness is really critical. On the mission level, on the other hand, timeliness is really not that important anymore. So if we just collect statistics and these statistics arrive a little late, it usually doesn't make a difference. So here timeliness is rather lax. The arithmetic challenge, on the other hand, is quite intense for mission level properties, because here we want to collect statistics. We maybe want to predict the behavior of the system or the environment. So the computations here are way more involved than on the sensor level, because here, since we have time critical computations, these computations have to be rather simple, and usually they are bound checks or just counting of values. The input data on the sensor level is usually really raw because we get data right from the sensor and we want to check whether this makes sense. On the mission level, however, it's more refined. So here we get data that is already validated and maybe even the result of sensor fusion of different sensors in the system. A canonical example for this is that on the sensor level, we work on data of the IMU or the GNSS module, whereas on the mission level, we already have a decent estimation of the current position, which is based on several sensors. And these sensors are distributed over the whole system. So the locality of the mission level properties is system-wide. We don't only check one thing in isolation as we do for the sensor level. Of course, there is not just this separation between sensor level and mission level, there's also things in between. For example, intercomponent checks. Most notably, this is like cross-sensor validation, where we want to check whether one reading makes sense by comparing it against the reading of a different sensor. So since these properties are kind of distributed on a full spectrum, the question is, can there be one language where we can express everything and monitor this perfectly fine? So is there this one language to rule them all? And the answer is pretty much no. So languages itself are, again, faced by a lot of trade-offs. So the most prominent trade-off is the question of guarantees versus expressiveness. On the side of guarantees, we usually have logics like LTL, where we have a decent understanding of how a monitor for such a logic works and what it does, what kind of requirement it has. And we get guarantees on its runtime behavior. On the other end of the spectrum, we have highly expressive languages, like general purpose programming languages. So for example, if you take Python, you can pretty much express anything in there, but you have very little idea of how it's going to behave during runtime. You need intensive analyses, or many of them even manual. So selecting the right language is really hard, and sometimes depending on the property you want to express, you need different languages to use. However, I already mentioned, what we are going to do is we will have a look at Artilula as a language and see what we can express with that. Things that are really interesting for the languages are, for example, the output quality. So if you, for example, take a simple logic, then the result most of the time is binary. So you get one output that says, okay, the trace was okay or the trace was wrong. And this is usually insufficient. So what we want to have is a stream-based language that gives us information all the time. So at any point in time where something interesting happens, like a new sensor reading arrives, we want to get an output, and the output tells us whether everything is going fine or not. So we have immediate feedback. And this feedback is better quantitative. So it's not just, yeah, everything is fine or not, so Boolean, but it's quantitative, telling us how wrong we are. This can be really useful when supplying this information either to the controller or when the whole mission is over to analyze how the system behaved. The next point that's interesting is the expressiveness. For the expressiveness, it depends on what kind of property you want to express. You need an expressiveness that is sufficient for this. And Artilula mainly focuses on arithmetic expressiveness. So arithmetic in logics is usually a problem and simpler in programming languages. And Artilula also focuses on clarity. So for example, logics are really concise, and this is pretty nice for short properties, because you only need a couple of symbols and you have to express everything and everyone knows what's happening. But as soon as the specification grows larger, logics tend to become kind of cryptic. And programming languages and also Artilula are different in this regard, because here we usually can still understand what's happening because everything is more modular. Then the next thing is the integration. Here it depends on what kind of system you have. So if you have an embedded device with really low resources like a microcontroller, then you usually don't want a solution, a monitor that requires a Java virtual machine, because it just can't run on the microchip. So here you have to choose what do you want. And also the general system architecture plays a role. do you have space for a software solution? Can you integrate a hardware solution? So here it depends on what you want. And RT-Loader provides a compilation to hardware and to software, which gives you a little bit more freedom than just having one compilation. In terms of integration, it's also interesting to see what is the resource consumption, because if the monitor is an embedded component, you should guarantee that the resource consumption in terms of space is always constant, or let's say bounded a priori. So RT-Loader does this. It has a guarantee that we only need constant space, and it also needs constant time per event. So this is a guarantee that's really useful to have. And the last thing I only want to talk about briefly is certifiability. The option to certify your monitor and your overall CPS becomes increasingly important. And for this, RT-Loader provides a software solution that is verified automatically. And there are some preliminary results for hardware, but this is something that's becoming increasingly interesting. I won't talk about it too much though. Okay, so this is a lot of information about languages in general. Let's just dive right into RT-Loader and see what is the language and how does it work. For this, it's easiest to just look at a couple of examples. So the first example here is the sensor validation. That is the sensor level property, which we already mentioned. It's that an altimeter reading must be non-negative. So in RT-Loader, what we have to do is we first declare an input stream, and the input stream is called altitude and has the type float 32. So it will always have the width of 32 bits, and is a floating point number. As simple as that. The output then declares that we want to raise an alarm if the altitude falls below 0. And in this case, the information, the message after that, is passed on to the controller. Okay, that's pretty simple. Let's have a look at a different specification. Let's say we have a barometer, and the barometer has to produce between 9 and 11 readings per second. So what do? First, we have to declare that there is this input called pressure, which gives us, once again, a floating point number. And our output readings per second then takes this pressure stream and aggregates values over 1 second and counts them. So the values that's produced by read PS is the number of values we got from the pressure stream over 1 second. That seems fine. Lastly, the trigger checks whether this value is between 9 and 11. Okay, great. The problem here is that there's this little annotation here which says at 1 Hertz. And this annotation dictates that the read PS stream is only evaluated once per second. However, the problem is that this is what we call isochronous. That means we know statically when these points in times will be. This sounds reasonable, however, it has a couple of drawbacks. So to understand this, first have a look at a simplified specification where we say we want to have exactly 4 readings per second, and we have such a timeline here. Now with our isochronous setting, we will check and count the number of values at every integral point in time. So here we always look back for 1 second and see, okay, everything is fine. We only have 4 readings in every interval of 1 second. However, when looking closely, we can see that there are intervals of 1 second, and in these intervals there are 8 readings rather than 4. And the property states that we need exactly 4 readings in any of these intervals. So checking only on integral points in time does not suffice. So the specification we have and the Lola specification are semantically different. And the point here is, if we remove the at 1 Hertz, then RT-Loader would reject the specification because it cannot monitor something like this. And that's interesting because it's a rather hard restriction on the language. And the question behind this is why? Why would we want to restrict the language like that? To understand the reasoning behind this, we have to have a look at the memory consumption. So consider this specification here. We say every request needs to be granted within 1 second. This is simply enough when we want to express it in MTL. Here we can just say we have a globally, so at every point in time. If there is a request, then we demand that there is a grant within 1 second. Perfectly fine. Now consider this timeline here. In the first second, there are a couple of requests, and and now we have to check whether there is a grant within 1 second. So the obligations the monitor has to maintain for MTL is, for every single request we get, we have to check 1 second later whether there was a grant. That means the number of obligations we have to maintain increases with the number of inputs we get within this frame of 1 second. And this in particular means that the number of obligations is statically unbounded, because we don't know how many inputs we are going to get. In RT-Loader, this is different, because here we know as soon as we get the first request at 0.07, we know 1 second later we have to check whether there is the respective grant. And everything in between is something we don't have to store. So here RT-Loader says, okay, we have to approximate, and we only consider this one obligation. And as soon as the obligation is completed, we can start a new obligation. So if there is a request after the point in time t equals 1.07, then we start a new obligation. And this obviously is not the same expressiveness, so there's a difference in semantics. But the point is, for MTL you need unbounded memory, and RT-Loader can guarantee that you only need bounded memory. So here RT-Loader restricts the specifier, and it does so to enable static memory bounds. And this restriction is enforced over the type system. I will first give you a chance to ask questions, and afterwards we continue with the type system.